Example number 1 wants us to suppose that x and y are functions of t, meaning that we could write x as a function of t and y is also a function of t. And we want to suppose that this relationship right here holds. We want to get, they're asking for us to relate dx dt and dy dt. This means we want to find x prime as a function of t, y prime as a function of t, and we want to find an equation or some relationship that compares these two guys. So I want an equation that's got these two guys in it right here, okay? Or you can think about it as these two guys right here. So how do we do that? Well, what we're going to do is we're going to take this function, excuse me, not a function, this relation right here, this equation, and we're going to differentiate everything using implicit differentiation. So the implicit differentiation that involves our chain rule. So what we're going to do is we're going to take everything, the derivative of everything with respect to t, because that's the guy we want with respect to, okay? So I'm going to take d dt of x to the fourth plus d dt of xy plus d dt of y to the fourth, and that'll be equal to the rate of change of 1 with respect to t, just like that. Okay, so let's go ahead and do this first guy here. Well, again, we need to have the variables be the same. They're not. And we know that x is a function of t, so let's go ahead and change this here to be dx dt times ddx of x to the fourth. Okay. Now let's do this green guy here. So again, I need to do this out right here using the product rule because I've got the product of two different functions. So this would be d dt of, so it's the derivative of the first times the second plus the derivative of the second times the first. So we'll get to that in just a minute. Then over here, this guy in purple, we need the variables to be the same. So this would be dy dt times ddy of y to the fourth. And that'll be equal to, now ddt of 1, that's just 0. Right? Because the rate of change, the derivative of 1 with respect to t is just 0, because this is a constant. So this right here is going to give me dx dt times 4x to the third. I need to make a variable change here using the chain rule. So I'm going to go dx dt times d dx of x times y. And this will be dy dt times d dy of y times x. So what I did here is, remember, you can think about these things to remember this. You can think about these things as canceling out. So I rewrote this like this, and then of course the multiplication of y follows at the end. Same deal here. If you cancel the y's, you get d dt, which is this guy, and then the rest is the same. This right here is plus dy dt times, now the derivative of this with respect to y is 4y to the third, and this is still equal to 0. Okay, so this is already set. I'm just going to write this guy out front. So 4x to the third times dx dt plus, now d dx of x is 1. So this guy right here is 1. So I'm left with 1 times y, which is just y, dx dt, like that. Here, Same deal. This guy, dy of y is 1. So this guy times x times this will be x dy dt. Plus, I'll bring this guy out front here. So this would be 4y to the third times dy dt. And that's equal to 0. So you'll typically put your like terms together. So I can factor out of here a dx dt. So I'm going to have the following. I'm going to have 4x to the third plus y times dx dt plus 4y to the third plus x times dy dt. And that is equal to 0. And so if you wanted to get dx on one side and dy on the other side to see what the relationship is, we could solve dy dt by itself. And this is good right here, okay? But we could move this guy over to the other side. So we would get 4y to the third plus x times dy dt, the rate of change of y with respect to t. That's equal to negative 4x to the third plus y dx dt. And so if we solve for dy dt, we get negative 4x to the third plus y over 4y to the third plus x times dx dt. So this is the relationship between dy dt and dx dt. So the relationship between how y changes with respect to t and how x changes with respect to t is given by this this equation.